everybody. This is Vector Control with our project, the Wastewater-based Epidemiology Optimization Algorithm. Before we get into the meat of the project, let's take a moment to introduce our team. My name is Mackenzie Hall, and I'm the project lead. I'm an electrical engineering major with a concentration in control theory.
Hello, I'm Christian Snowden. Similar to Mackenzie, I'm a controls and automation concentration. My primary role was to manage documentation of our project and its code.
Our project is designed to aid health officials in a pandemic by optimizing the selection of sampling site locations within a sewer network during wastewater-based epidemiology or WBE studies. Our algorithm can be applied to any given wastewater network and will output the node testing sites that will maximize the total viral observability of the sewer network. Remember, observability is the ability to see the states or viral loads of a node within a system. The algorithm is currently set to trace COVID-19 viral parts, which are shed naturally in the feces of those infected, but it could be set to trace any virus.
We followed closely to our original plans, with some reversal, but sadly some of the best visual elements didn't make it. Instead of highlighting sensor locations on a map, we chose to print out a list of optimal sensors. We also decided not to use ArcGIS for global coordinates because we didn't have access to public network or the time to connect the program. Instead of creating a custom algorithm, we were able to adapt an open source algorithm created by Shen Wang, a UTSA doctoral student and one of our mentors, which saved us an immense amount of time for joining all our functionalities. Given our goals and our results, here we have our major components in a diagram in the bottom right explaining how they interact, which I would recommend your focus be on. PySwim and MatSwim are both ways of interfacing and deriving data from SWIM, aka the Stormwater Management Model. Despite its name, SWIM is also used for sewer modeling, so it's used extensively when extracting our quality model and using for our hydraulic model.
The state space quality model we developed was the main bounty from the hydraulic modeling of SWIM. Our states here are a vector containing the viral load, aka quality, of each node in the sewer system. The matrices are simple, even though deriving them took some work. The A matrix contains the decay factors for the virus. The B matrix maps possible viral input locations in the network, and the C matrix denotes our possible testing sites. The D matrix is filled with zeros. It's notable that we used the packages SciPy and SciPy, which uses system magnification, to extract the output of our model, which we then compared to the validated SWIM output to ensure our accuracy.
In order to utilize our software, there are some initial setups required to ensure the model works properly. For example, forgetting to initialize the decay factor would result in nothing worth using. This was a mistake made in running our larger model, Red Chickasaur. Oh, wait. There we go.
The quality modeling of nodes is obviously one of the major parts of our project, so it's something we researched very carefully. The ODE you see before you was something we saw in multiple papers using WBE for COVID tracing, particularly the Hart and Holden papers if you're familiar with them. The Q represents the viral load in viral parts per liter, and the K represents the decay factor, how much of our past viral load is being lost as it travels through the sewer. We get this K value by doing some calculations involving sewer pipe length, flow time, and initial viral load, and then we store it in the A matrix. Each node has a different K, of course, due to the varying distances from viral inputs and also variations in travel time. These factors inform our quality state space model to ensure it behaves in a similar manner to the real network, which is very important since this model is being passed into the optimization algorithm, which will of course tell us our best COVID testing nodes. Remember, the open source algorithm we used here seeks to place sensors, aka COVID tests, in such a way that maximizes the observability of the quality model. Here we have the results for the input network called 3 tanks, which you can see on the bottom left. It's a relatively simple network with 13 nodes, so it's a bit less complex than what you'd see in a real city. The initial best testing nodes are circled here in orange, and the one circled in red, known as DES1, is the best node for the rest of the time steps until the end of the simulation, in our case 144 hours. It may look weird that the best testing node is at the end, but remember that this is a system that is not very complex in its hydraulics, and is governed almost completely by gravity. The predictability of flow is a boon to our analysis, and therefore the sensor placement at DES1 makes a bit more sense once you think about it. We will see a live demonstration of the code behind these results in a moment.
Alright, so moving to display the code, I'm going to run it quickly while I go over some functions and pull up another side. So we're going to start off here at all the way up at line 28, which starts our PySwim get nodes and links. This allows us to create matrices in a format that works well for our state space modeling. Scrolling down a bit further, we get to our get length. This was one of those features that was not available in PySwim and had to be user defined. It isn't the most clean way, but it gets the job done. Scrolling further, we have our branches, which is used for getting the length of all paths. It basically traces a start to end node and finds all of its ends. Scrolling a little bit further down to, it was line 385. We have the start of our step and sim, which is a PySwim functionality that allows us to step through the system to get our COVID pollution values and which are viral loads, and to compare those to our graph in the future, as well as extract the values that will be used to get our state space model itself, which is seen a little bit lower. But for the sake of time, we will go ahead and run the actual algorithm in of itself. So this algorithm was taken from moving our state space model into a file that we then use the optimization algorithm on. Down below you can see that there are a list of sensors that index where they would be inside of the matrices I talked about in the all nodes before. Obviously our stuff could use some work. It is a proof of concept. And with large files, it can take a lot of time, especially like with Red Chickasaur, which took 3 hours and 15 minutes to calculate. 3 days worth of samples. The code itself could use some optimization through possibly parallel processing and tweaking the routing step to balance precision and processing time. And if we could adapt the algorithm into Python and specific to SWIM models, it would make a more robust utility. Thank you. If you have any questions, see us in the later questions time.